Okay, so what we started talking about on Friday is this concept of Hess's law and energy cycles, the idea that no matter what path we take to get from point A to B to point B, the change in enthalpy is going to be the same. The net displacement on a map is going to be the same whether you take it as the crow flies versus taking a winding road. And so we use this to be able to find the change in enthalpy of reactions for which we can't directly measure it. And so there's sort of three versions of this that we're going to talk about. So on page 18, it sort of starts talking, we're going to jump around on the pages because I don't quite love the way he puts this section together. But the idea here is, for example, say we want to know the change in enthalpy of this reaction here going from our reactants, going from these reactants to these products, but we cannot actually get this number. Well, we can if we know the enthalpies of an intermediate reaction where these same reactants go to essentially form our propane. So for example, this would be an enthalpy of formation. We'll talk about this in a minute. If we can get the enthalpy of formation of the propane, and also the enthalpy of combustion of the propane, both of which we have in standard tables, we usually have those data for certain compounds, then we can basically add those together because we're traveling, we're just taking a two-step, and so we're adding the enthalpies of the two steps together to get what would be the enthalpy of the direct route. Okay? So if we are traveling in the same direction as the arrow in our enthalpy cycle, in our little triangle here, then it is going to be a positive. It's not necessarily going to be a positive number, but it's going to be that delta H. If we're traveling in the reverse direction, then we have to reverse the sign. So if we're going, if we're traveling in the reverse direction from the reaction that we know the enthalpy of, it's just a matter of changing the sign, flipping the sign. And here's how that's going to work out. One thing that we can use in order to calculate these enthalpies, changes in enthalpy that we cannot directly measure, is the enthalpy of standard enthalpies of formation. So standard enthalpies of formation are basically, sorry, let me just skip here. If you look at, sorry, I'm going to make you flip back again to page 13. Standard enthalpies of formation is the enthalpy change when 1 mole of a substance is created from the elements that make it up in their standard states. Okay? And the standard state is the normal, pure, stable state measured at standard pressure, which is 100 kilopascals for IB. And we can look up these numbers in a table in your data booklet, for example. And I believe we started talking about the fact that the enthalpies of formation are always pegged to 1 mole of the product. So we're using a balanced equation, but the coefficient of the product that we're making is always 1, which means that sometimes we're going to end up with halves as our coefficients, which you've learned in the past. We never do that, except that sometimes we do it, and this is one of those times, okay? Because we want to know what is the equation per 1 mole. Which is why our enthalpies are always kilojoules per mole. And in this case, it's per mole of the substance that we're creating out of the elements. Okay, so we sometimes are going to get those fractional coefficients when we're talking about, when we're writing an equation for the standard enthalpy change for formation. So if we want to write an equation for the formation of 1 mole of a compound, we have to think about what are the substances, what are the elements that are going into that compound. So for propane, for example, one of our substances is going to be carbon. Carbon in its standard state at room temperature and atmospheric pressure is a solid. That's an S. Sorry, I have trouble drawing S's on this board. All right. And the other part of the propane is hydrogen. Hydrogen is one of our diatomic elements, so it's always going to be H2 in a chemical equation, which is a gas. Okay. And that's going to give us 1 mole of C3H8, also a gas. Now, I have to balance this, though, because it's not currently balanced, and we have to make sure that we have enough of our reactants. So I'm going to put a 3 in front of the carbon, and I'm going to put a 4 in front of the H2 to give me a total of 8 hydrogens. Okay. So that's really all it is. If you're asked to write an equation, you take the individual elements, find their standard state, which for most things is going to be a solid. Mercury and bromine are the only liquids, elements that are liquid at a standard state. The gases are going to be all of the noble gases, obviously, although they're not going to make any compounds that you're going to be asked to talk about. But hydrogen, nitrogen, oxygen, fluorine, and chlorine are all gases. And I believe that there is in your data booklet, yes, there is a periodic table with melting points and boiling points. So if you forget whether something is a solid or a gas at standard state, it will give you the boiling point, and you can see are we above the boiling point, in which case it's gas at standard state? Are we below the melting point, in which case it's a solid at standard state? Okay, so this is the kind of thing that you might have to do or might have to interpret for this enthalpies of formation. So how do we use enthalpies of formation? Well, we can look at, I'm just going to clear this. We can look at our reaction that we're interested in, okay, going from our reactants to our products, and we do not know the enthalpy change for that reaction, but we may know the enthalpy changes of the formation of our reactant substances and our product substances. In which case, we're basically going to draw a triangle with our reaction of interest across the top, and then going from the elements in standard state to the reactants and to the products. Okay? And this is going to be the sum of the enthalpies of formation of all of our reactants if we have more than one. And this is going to be the sum of the enthalpies of formation of all of our products if we have more than one. Now you'll notice that the arrow goes up in both cases. That's because we are forming those substances from the basic elements. So both of those arrows are going to go up to both corners. Okay? But when we're trying to add up the enthalpies, we are going from the reactants to the elements and then the elements to the products. That's the direction that we have to go in to get the change in enthalpy in this direction. Okay? And so this one is going to be going against the arrow for the enthalpy that we know. So we are going to flip the sign on our reactants, okay, on the sum of the enthalpies of our reactants. The products is going in the same direction in our enthalpy cycle. So we are not flipping the sign for the products. So since the net is the sum of the parts of the path, we can either say it's the negative sum of the reactants plus the sum of the products, or we can just write it as products minus reactants. That's saying the same thing. Whichever one makes the most sense to you. Okay? I suggest that you practice drawing these enthalpy cycles, because if you're stuck and you're not sure which way to go, the enthalpy, the triangle will help you. All right, because you got to think about what am I doing? I'm going from the elements to the substances in the equation, so that's going up. All right, and then if we're traveling in this direction, we're minusing the reactants or flipping the sign on the reactants and keeping the sign on the products. Okay. So in your data booklet, tables 11, 12, and 13 have standard enthalpies. 11 is bond enthalpies, which we'll talk about a little bit later. 12 has a number of thermodynamic things, some of which you don't need to know for standard level, like the entropy and Gibbs free energy, but it also has standard enthalpies of formation. And then table 13 is enthalpies of combustion, which we'll talk about in a sec. Okay, so they're all kind of in the same place in your data booklet. Sometimes you will be asked to use the data booklet. Sometimes they will give you a table of the relevant enthalpies that you need to use, and you just have to figure out how to plug them into the equation. Yes? You have the data booklet for paper 2, so not for paper 1. So if you're asked something in paper 1 about something like this, they will give you a table, or they will give it to you as the enthalpy of formation of this substance is X, and the enthalpy of formation of this substance is Y. Now, how would you set up the equation to give you, and it would be like X minus Y or X plus Y, something along those lines. So if it's necessary, they will give you whatever you need in paper 1 to answer the question. But if you're being asked to calculate something in section 2, in paper 2, then you will have the data booklet. So paper 1, you get just the periodic table. Paper 2, you get the data booklet and a calculator. Okay. An important thing here is that if you have just a plain element as one of your reactants or products, like iron, Fe, just as a reactant, that is already an element in its standard state. The enthalpy of formation of that is 0. That is also the case with our diatomic elements. So can I put this back up here? So all of the 7 diatomic elements that exist as molecules of 2 atoms covalently bonded together, those are also already in their standard state. So O2 is already in its standard state. You would never have an enthalpy of formation of O2 from just O, because it's only going to exist as O2, well, primarily for our purposes. Okay. So that's our mnemonic for the diatomics. I have no brighter, clever friends: iodine, hydrogen, nitrogen, bromine, oxygen, chlorine, and fluorine. Also, there are 7 of them, and they make a 7 on the periodic table, and then you add hydrogen. Either way that you can remember it. Okay. So here is an example exercise 1. I believe this is on page, nope. Yeah, so this is on page 14. So you have a table of a whole bunch of compounds with their delta H's. Notice they have different signs. Some of them are positive. Well, one of them is positive. A bunch of them are negative. They have different numbers, the different degrees of negativity. The lower the enthalpy of formation, so the more negative, the more stable that product is, because it's the lowest on the sort of energy diagram. Okay, so say we want to calculate the enthalpy change for this reaction, for this combustion reaction of pentane. It's going to be products minus reactants, because again, our products are going to be the same sign, our reactants are going to be the flipped sign. So we need to know what the enthalpies are for the products and the reactants. There are a lot of different ways you can do this as far as the calculations go. I like to find what's in the table and kind of put it next to what I'm looking at. So the pentane is negative 173. This is all in kilojoules per mole. O2 is not in the table. Why is it not in the table? Why don't we have a delta HF for O2? Yeah. What? It's 0, right. It's because it's already, O2 gas is already the standard state for oxygen. Okay, so this we don't even have to consider. We could call it, or we could call it 0. Okay, over here, CO2, negative 394, but I need 5 of them, so I'm going to multiply that by 5. Okay, and the H2O, same thing, negative 241.8, 1.8 times 6. Okay, so I've got my reactants are at negative 173. Our products are having to distribute these and then add them together. It's because it's the sum of the enthalpies of formation for each of those. So if I go ahead and do this, punch this in, 395 times 5, so that's going to be negative 1975. And that this is going to be, I'm going to add my 241.8 times 6. That's going to be negative 1450.8. Okay. And what I want for my delta H of the reaction is going to be the sum of the products minus the sum of the reactants. So that's going to be these two added together. So that's going to be negative 345.8. And then subtracting the reactants, which was negative 173. So that's essentially adding 173 to that. I'd come up with 3252.8. Please tell me if I'm doing the math wrong, because sometimes I do that. And that's going to be kilojoules per mole. So it's really just knowing how to set up the equation and then plugging and chugging. That's all there is to it. And you just have to be very careful, both when you're transcribing these and then also when you're punching things into your calculator, that you're keeping the signs the way they need to be. Oh, and sorry, that's a negative sign. Sorry, negative 3252.8. That should be the correct answer. So it's not, none of this is difficult. It's just remembering how it goes, remembering what thing is being added, what thing is being subtracted. Okay, and that's just, like I said, the drawing the triangles can help with that. Or if you're more of a rote memorization person, remembering that formation is products minus reactants, and then remembering what that relationship is for each of the other ones as well. Okay. And you can, set up the punching it into your calculator however you want. You could do the whole thing in one go. You can break it apart into pieces to make sure you're keeping track of which number is which, whatever works best for you. Okay. All right, so that's one way, enthalpies of formation. Another thing we can do is it's often fairly straightforward to burn things. You can usually get, data from burning things. So we tend to have tables, lots of data on enthalpies of combustion. And so basically, what we're going to do the same thing. Instead of forming our reactants and products, we're going to burn them. We're going to burn our reactants, and we're going to burn our products, and we're going to capture those data and then use that in our enthalpy cycle. Now, we're not actually burning them. We're just saying we already have a table of the data for the enthalpies of combustion. This one is going to be reactants minus products, and I'll show you why. So before, we had simple elements going up to our reactants and going up to our products. But now that we're burning everything, we're going down from our reactants to the products of combustion, and we're going down from our products to the products of combustion, because we're burning both sides, okay, theoretically. So we have an enthalpy of combustion for the reactants going this way, and we have an enthalpy of combustion for the products also going down this way. But now, again, we need to follow the route that's going to get us from reactants to products. So we're going to be traveling this way, which is along with the sign of the enthalpy of combustion. And then we're going to be traveling this way, which goes against that enthalpy of combustion. Okay? So now it's going to be reactants minus products instead of products minus reactants, because we're switching the direction of these arrows and we're switching which side has to be reversed. Okay. So it's exactly the same thing, except that it's going to be sums of the enthalpies of combustion of all of our reactants minus the sums of all the enthalpies of combustion of all of our products. But it's basically the same thing. So it's just, again, setting up the equation correctly and then plugging the numbers in. Okay. Let's actually skip to one that's in your booklet. Page 15 in your study guide. Again, it gives you the reactants minus products. And here's an example. So we've got C2H4, our ethene molecule. We are reacting that with hydrogen to give us ethane. And we don't know the enthalpy of this reaction, but we do know the enthalpies of combustion of all of the pieces. So we're going to theoretically burn all of our reactants and our product because we happen to know these enthalpies, okay? So we're doing sum of the reactants minus the sum of the products. Our ethene, is negative 1411. And this doesn't have units, but you can assume it's kilojoules per mole. Plus our hydrogen, negative 286. Okay. So that's our reactants. That's the sum of our reactants. And then we're going to subtract the sum of our products. We really only have one product, and that's going to be negative 1561. I guess I could have made that regular parentheses. But that's really all there is to it. So then it's just a matter of plugging it into your calculator correctly. Okay? So the enthalpy of our reaction is going to be that equation. This didn't have any coefficients. It's already balanced the way it is. So we don't have to multiply anything. We just have to add and subtract. Okay? So I'm going to take my 14, 11, 286. 1. Did I do that right? Let's try that again. Negative 14, 11, minus 286, 25, plus 1561. Okay. So again, if I did the math correctly, if I punched it in correctly, it should have 436 kilojoules per mole as our enthalpy of reaction. Let me know if you got something different, because that certainly happens. Yeah. Negative 136. Let's see. 1411. Negative 1411. Plus negative. I may have messed up the signs. Minus negative 1561. Yep, you're right. I don't know what I did there. Sorry about that. Negative. Yep, I agree with you. It's negative 136. I probably failed to subtract there. Anyway, and you can, you can sometimes check yourself just by kind of looking at how you set it up to see if it should be a negative or a positive number, but that's really all there is to it. So it's remembering that our route that we're taking is in the correct direction for the reactants and the opposite direction for the products, which is why we subtract the sum for the products. So formation and combustion are going to be opposite. Formation, products minus reactants; combustion, reactants minus products. Okay? But the same basic idea. Same setup, essentially, just remembering which one is subtracted. Okay, and then the last thing that we can use to calculate theoretically an enthalpy of a reaction that we cannot measure empirically is we can use bond enthalpies. Bond enthalpies are the energy contained in a bond that is how much energy it would take to break that bond. And the numbers that you get, for the most part, with basically one exception in your data booklet, are averages. And that's because when we talk about something like an oxygen-hydrogen bond, the actual amount of energy it takes to break that bond, break 1 mole of bonds of the substance in a gaseous state, which is the technical definition. The gaseous state matters for things like this and ionization energy and other stuff, because when molecules are in the gaseous state, we don't have to deal with intermolecular forces and lattice energies and things like that when we're talking about breaking bonds. They're just separate molecules bouncing around by themselves. So you can imagine that we have an OH bond here in methanol, we have one in butanol, and we have one in octanol. But actually, the amount of energy it takes to break that bond is going to be slightly different, depending on the context. So it's going to be a little bit different between all three of these molecules. And even in a water molecule, we've got 2 OH bonds. The energy to break the first one is about 502 kilojoules per mole. The energy to break the second one after the first one has been broken is a little bit less, 427 kilojoules per mole. Okay? Bond enthalpies are always going to be positive because it takes energy to break bonds, just like it takes energy to snap a pencil in half. And it takes more energy if you have a thicker pencil, or if you have multiple pencils together, it's going to be harder to snap them in half. Same idea. So even within a molecule that's as small as a water molecule, there are differences. And so if we average those numbers, we end up with something in between, obviously. And if you look at, say, the averages for the 2 OH bonds in water, they average out to about 464 kilojoules per mole. And the data booklet gives you an overall average of 463, so pretty close to that. But that also includes a lot of other compounds that have an OH bond that could be broken. All right, so the values that are in the tables that you have in your data booklet or that you might find elsewhere, values for bond enthalpies, are average values. And so it's not going to be perfect. Okay, it's going to be a good estimate, but it's not going to be perfect. All right, so if you look at page 20 on your study guide, there's our definition of the average bond enthalpy. Bond breaking is endothermic, meaning we have a positive delta H. Bond making is exothermic. Okay, so if we think about a substance where we have, if we think about this less, I don't like to use the triangle for this. I like to use an energy diagram. It just makes more sense to me, but you could use a triangle as well. Essentially, we have our starting substance, and we are our reactants, substances, and we are putting energy in to theoretically break every single bond in our reactant molecules. Now, that may have nothing to do with how the reaction actually goes, the reaction mechanisms, but reaction mechanisms are actually kind of complicated, so basically we just make the assumption that we just have single atoms up here. And that includes anything that is a diatomic. So O2 would break down into two individual oxygen atoms. Okay, so we're putting energy in to break all those bonds. And then we're getting energy back when we form the new bonds for our products. So either way, regardless of whether this is a exothermic or endothermic reaction, regardless of the relative locations of the reactants in the products, we're still going to be putting energy in to break the bonds and getting energy back to form the new bonds. Okay? And so that is why we are also going to essentially be reactants minus products for bond enthalpies. Because we're summing up all of the enthalpies of the bonds of our reactants, and then we're subtracting the sum of the bond enthalpies of our products. Okay? So, you can think of it as this is like combustion. You can think of it as these two are the same and formation is different. You can think about it as drawing the cycle and find the direction that makes sense. Whatever works for you as far as remembering which is which. Okay. One disadvantage to this is, like I said, the average bond enthalpies aren't going to be 100% accurate for those specific molecules. Okay. However, another disadvantage is that in order to do this, you have to be able to count the bonds, which means you have to be able to draw the structure. Okay, so this is where don't forget about your Lewis structures, because A, there'll be questions about those on the exam, and B, you're going to need them to answer a question like this. So here we're looking at the combustion of propane. Theoretically, we should actually have this enthalpy of reaction because it should be in our enthalpies of combustion table, but if we are asked to calculate it from bond enthalpies, then this is how we would do it. We would say we've got 3 carbons, we've got 8 hydrogens. I have not seen an example, or at least I haven't noticed an example where it would be something that would have isomers. If it did, it wouldn't matter because it's still the same number of bonds, the same number of the same type of bonds. You're going to have to remember that, for example, O2 is a double bond. That's going to make a difference, okay? Because a double bond is going to have a higher bond enthalpy than a single bond. You're going to have to remember that carbon dioxide has 2 double bonds. I strongly suggest writing out every single structure of every single molecule so that you make sure that you remember what the bonds are and how many there are. So I'm looking at this and I'm seeing I've got CC bonds and I've got CH bonds. Okay. CC bonds, I've got 2. CH bonds, I have 8, right? 1, 2, 3, 4, 5, 6, 7. Yeah, 1 for each hydrogen, duh. So I have 8 of those. Here, I have OO double bond, and there's only 1 in each molecule, but I have 5 of those. So I've got 5 OO bonds. Over here, for my carbon dioxide, I have CO bond, double bonds. I've got 2 for each carbon dioxide molecule times 3 total carbon dioxide molecules or moles. And so that's going to be 6. Okay. And then over here, I've got OH bond, single, and I've got 8 of those because I've got 2 for each molecule and I've got 4 molecules. Okay. So then I would look in my data booklet, which I have somewhere here. Just had it this morning. Where did I put it? Well, it's here somewhere, but I'll just grab another one. And I'm going to go to section 11, where my bond enthalpies are. And you'll notice it's in a table with one element on the vertical and one element on the horizontal, and you just go to where they meet. Double and triple bonds are on the bottom. So notice that, make sure that you're getting the double and triple as needed, okay? So this is going to be 2 times carbon-carbon, which is 346. 8 times carbon-hydrogen, which is 414. 5 times double bond oxygen, which is 498. Okay. I'm going to sum all of those together. Okay. And then over here, I've got carbon-oxygen double bond, 6 times 804. And 8 times oxygen-hydrogen, which is 463. So I'm going to sum all of these, okay? And then I'm going to sum all of these, and I'm going to subtract. And that's going to give me my enthalpy of reaction. Okay? Sometimes you can check yourself based on what type of reaction it is. This is a combustion reaction. What should the final sign of my delta H be? Negative or positive? Negative, because a combustion reaction releases energy. So if I don't end up with a negative delta H, then I did something wrong. Okay? That you're not always going to be able to tell. But what you might find in a paper 2 question is they might say, either give it to you or tell you to look up the enthalpy of combustion of propane, or do this reaction with enthalpies of formation, and then do it again with bond enthalpies, and then compare the two, and talk about why they might be different. The answer to why they might be different is that these are averages, among other things, but that's the main difference. Okay? All right, and that is it for topic 5. We will do a little bit of equilibrium tomorrow. So have a great rest of your day, and I will see you tomorrow.